Hello, my name is Roberto Peon. I'm one of the co-inventors for SPDY. Welcome. If you are here to hear about SPDY, well, you are in the right place because it's here. So, what we're going to talk about? We're going to talk about the past. We're going to talk about what the world looks like today. What is SPDY? How to optimize for it? Where we're going in the future? And then we'll talk about stuff that's either supporting it already or that you can use to get it working. And then I'll go over an example of adding server push. So, the past. In the beginning, the speed of light was c. Okay, well, let's try again. That's a little bit too far. So, in the beginning of the web, we had HTTP 0.9. And, well, that's what we call it now. It didn't have a name there. In 1991, it was defined. And basically, HTTP 0.9 was a request get HTML protocol. There was no images, no anything else. And very soon after, in 1996, we got HTTP 1.0, and it brought in headers, including on responses, and servers could reply with errors, and clients could now upload data, not just in the URL, but with posts, and they could indicate that resources were going to be cached, and lots of other good features. Shortly thereafter, 1997 and 1999, so basically they got to work on it immediately, we got HTTP 1.1. And HTTP 1.1 gave us persistent connections, which is great. It also gave us chunked transfers, which allows us to send responses that don't necessarily have their size pre-computed before we've begun the response. So, in 1999, pages were very different. Specifically, they were tiny. They were around 60K on average, and at that time that was probably good enough. And I'll show you what Google looked like in 1999. Here it is. Google, this page here, was between 13K compressed and 14K uncompressed. It was tiny. Okay, so what does it look like today? In 2012, here you go. This page is around 200K compressed, and with uncompressed it's around 600K. This is a big difference from 14K. So today, pages are a lot bigger, and they're composed of more resources using a bunch more domains, and I'll get into exactly how many on average soon, and they're far more dynamic. And because of something that's about to come up, security is a much bigger concern than it was. And of course today, the speed of light is still c. It hasn't changed, and that means that RTTs are not going to be going down because, of course, we haven't made the speed of light any faster, and the speed of light actually bounds RTT. So here, let's look at the effective bandwidth as RTT decreases. You'll notice that the bandwidth goes up quite a bit more as we decrease RTT than if we just simply add bandwidth to our communications. So on the right-hand side here, we see effective bandwidth of HTTP if we add more speed to the connection, right? We're widening the pipe. And basically we look like, it looks like we kind of top out at around 1.6 megabytes a second here. Whereas if we look on the other side, we achieve that by decreasing latency to around 30 milliseconds or so. 50 milliseconds or so. So RTT actually ends up mattering a lot. In 2010, which was about a year after we started doing all this, a web page was about 702K on average, used about 74 individual resources, and it talked to about 10 different domains. And today, bigger, more, okay? And now, as compared to 1999, as compared to 2010, the stakes are higher, more people depend on it, and more specifically, because of this, you probably depend upon it. So, SPDY, it's here. What is it? I've heard this question a number of times today as I was talking to random people. It's a session layer replacement for HTTP. And, well, so why? HTTP, it's been here for a while. It's been here since 1999 in its current incarnation. Why do we care? Well, you should care because the idea is that it's going to make it faster, it's going to make it more secure, and it should be doing it with less effort on your part. So I've spent some time trying to do some web page optimization. God, that's pretty hard.
you have to keep a lot in your head, and you have to know a lot about who your customers are, where they are, how far away from you, what their links are like, what their packet loss is like, how the particular set of browsers that they are using are going to interpret the resources when you get it. It's a big, really difficult problem. I'm hoping that we can make some of this easier, and as a result, make web pages faster, because we should be doing things that make it faster for you when you do it the way that you think is most forthright. Right? We shouldn't be making it so that you have to do all this complex stuff in order to get a page that is performant for your users. Okay, but no guarantees. So how does it work? So first of all, it's always over TLS. So you can have HTTPS schemes in your URLs, and it can be speedy. You can have HTTP schemes in your URLs. It can still be speedy, although we don't do the same certificate checks for those resources. It's still going to be better than HTTP, because you're at least going to get point-to-point privacy. So if you're in a web cafe and somebody is sniffing, you never know, right? If you're using Speedy and that HTTP resource is going over Speedy, then that person doing the sniffing isn't going to be able to catch it, right? That, I think, is pretty cool. So that's not the only reason, though. Has anyone experienced this? Transparent proxies get in your way all the time. You think, you know what? I've deployed my own application, let's say on an Android phone. It does some HTML. I control it. Got the server. Control that too. Surprise, compression doesn't work. Surprise, other things happen. Okay, well, the truth of the matter is, on port 80, despite the fact you think you own both sides of the connection, transparent proxies are in there. They're mucking with it. They're changing stuff. This basically makes it really hard to deploy anything new, whether or not it's part of the HTTP 1.1 spec, as on port 80. And actually, just so you know, it makes it really hard to deploy HTTP 1.1 on port 80, because the subset of HTTP that people actually speak on port 80, it's not the full subset. All right, so another fun bit. Firewalls, great for security, great for keeping the stuff you don't want out. But of course, you have to know you don't want it. So most firewalls they're open on port 80 and 443 by default, and that's the world as it exists. So, as I mentioned before, if you're always over TLS, doesn't matter what the scheme, then all the various requests that you make will have that kind of security. Speedy does header compression. So if you've ever looked at the HTTP request stream, for instance, you've brought up the dev tools in Chrome, you will see that a lot of headers. And it's a lot of text. And it's text. And you will see that most of the stuff is repeated over and over and over again for every request. As an example, your user agent. Yeah, you know, I've noticed that my user agent doesn't change terribly often over the lifetime of a connection from my browser. Yeah, no, not really. Except encoding, pretty much the same. All of these other things don't change. The version of the connection, generally doesn't change. At least over Speedy, you're guaranteed it's a full end-to-end connection, so it's not going to change, right? All this stuff means that we're sending a lot of information over and over again that we really don't have to. So, as I said, much of the headers are repeated. I mentioned user agent. Thought about the cookie yet? How big is that cookie you send on every request, every time? I've seen, they're pretty big, at least they can be. I've seen cookies in excess of 32K. It's really cool when that ends up being represented by 1 byte. Much faster. All right, HTTP methods. Most of them are GET. Some of them are posts. Yeah, I don't know why we just keep using all those characters for that every time. And of course, the HTTP version string, mentioned that, right? /r/ns, the end of every line. Every line, 2 bytes. Why? All right, okay, and there's more. So, how effective is it? Well, on the first request, on the left-hand side of this graph, we see it's somewhere between 10 and 40% on the first request. That's pretty good. On subsequent on subsequent requests on the same connection, you can get much better. For instance, looking at this, we see that generally between 80 and 99% compression, with a big spike around 97%. I think that's pretty good. because I think that most of the stuff that's in the headers isn't actually useful most of the time. So we shouldn't be penalized for it. All right. So, mobile. I've noticed a whole lot of excitement over an Android. Got one in my pocket. I like it too. But I've also noticed that the net connection, despite all the promises I've been getting, it's really not that fast. And it seems to be a lot faster in the upload direction. Wait, okay, it's slower in the upload direction, haha. Okay, so this actually really matters for requests because most of what you're sending isn't going to be a big upload from a mobile phone. Sometimes it is. Sometimes you've taken a wonderful video of your daughter or something like that, and you're going to upload it, in which case you probably don't care about latency. But if you're doing web stuff, you're sending requests. And generally, there's not a big post body attached to them, so the headers end up being most of it. And when you're opening up your connection, because of the way TCP works, it's going to throttle you down. And it's going to throttle you down early, and it's going to learn over time, and it's going to open up that window slowly so that we don't cause congestion and a cascade failure of the internet, which would be bad. So it's probably a good idea. But if we put more relevant information in the upload direction, we're more likely to get responses in the download direction by the server sooner. So that's the basic idea. All right. It's binary framed. Now, if you're writing a web app, this isn't going to matter. But if you're deciding that you're going to modify your server or a client to speak Speedy, it's a lot easier to write a binary protocol than it is to parse HTTP. And having written a few HTTP parsers, it's a lot easier. Okay. So it's also faster to parse. It's a nice benefit. It's not a huge deal. HTTP parsing shouldn't be taking up any major amount of time, even if you're doing it in interpreted language. It's the complexity of writing it that's the hard bit. It's multiplexed. It's multiplexed to the tune of, let's say, we can support around 1 billion on one TCP connection. Now, I mentioned the average before. The average is around 80-something, 84, I think it was, requests per page. So we have some runway. And if we decide in the future that we don't have it enough, 1 billion is not enough, we can add another opcode, define another frame type, and there we go. And the way the protocol is spec'd out, that should basically be backwards compatible because we'll be able to figure out whether or not that'll work in the handshake, and we can reject individual frames if we have to. Unlike HTTP, SPDY is full duplex bidirectional. So any stream can be sending and receiving simultaneously. This will make things like layering WebSockets over, if we ever actually get to it, really easy to do. And this will allow us to use the one TCP connection for all of these things. Right? So we're trying to plan not just for HTTP, although we think that we can get a lot of benefit for HTTP, but we're also trying to plan for other things in the future that will allow us to do more interesting things for you. Okay, prioritization. I don't know how intently you've looked at things, but you've probably done it. And you've probably been curious because you see the request go out, you see the response come back, and then there's this period of time where nothing appears to happen. The browser isn't sending any requests. Well, what's happening there is the browser is actually doing something that's really smart for you for HTTP. It's looking at it and it says, aha, I haven't quite finished receiving that CSS or JavaScript that you requested as part of the page. I'm not going to request these images yet. Because in HTTP, if you're connected to 10 different domains, maybe you have, well, 12, let's say, maybe you have 70 some odd connections. There's no way of throttling the server when it's sending you those images. And as a result, those images are going to compete with your bandwidth for the important resources. So the browser is doing you a favor. Now, if you have a way of coordinating all these things, and you have a way of saying, this is higher priority, for instance, give me my HTML before you bother to send me the images, give me the JavaScript before you bother to send me the images, etc., then the browser doesn't have to do this heuristic. Instead, it can send all the requests to the server, and the server can keep filling up the pipe whenever it's empty with the most important thing that it can find to fill it up with. SPDY also does interleaving. Now what this means is that if I start downloading a video of my daughter and my boss calls me up and tells me one of the servers isn't working, I can open up a new tab in my web browser to the same thing and start looking at the site. And the server will be smart enough to pause that download for me. and it'll pause it only so long as it has more important things to send. So interleaving means interruption. We can interrupt any of the streams at any point in time if we have something more important to say. And it also means that we can say things in parallel. Now what this means, effectively, is that if your server has decided to think for a long time about something, it's not going to slow down all the things it doesn't have to think about for. And this ends up being a very interesting problem for HTTP called head-of-line blocking. You're probably familiar with it. We don't suffer from that with SPDY because of interleaving. All right, server push. Now we're just beginning to play around with this. And frankly, I'm really excited about server push. Server push gives us much better control over every aspect of our transaction. And in particular, unlike inlining, which allows us about the same latency win on the first request, it allows us to put stuff in the browser cache. It's referred to by its name. That means on the next page load, and I hope that you guys are planning to have the customer come back to the page, so this should matter, right? Is there anyone here that doesn't hope that the customers come back to the page? Sometimes silence is golden. So, on the second page load or subsequent, having these things in the cache can be a great benefit. Don't know about you. What do you guys think? Is inlining annoying? Well, I think it is. So, one of the reasons it's annoying is despite the fact it shaves off an RTT, it's really, really easy to get wrong. If I accidentally inline an image, for instance, before that critical JavaScript, I've just ruined my user experience. And what works today for inlining my page doesn't work tomorrow necessarily because one of the resources may be written by a different developer than the other one. And unless we have some mechanism that allows us to redo the order in which we're inlining every time we've changed one of the resources, we may be getting it wrong. And that is fairly often, unfortunately. All right. And as I mentioned, beginning to make its way into implementations. And again, you'll see that in the demo soon. All right. I've heard people arguing against server push, and I think that they need to think about it a little bit more. The way I think about server push is that server push is much better inlining. It's inlining that is forgiving. It's inlining that when you make a mistake and you include an unimportant resource because of the interleaving and the prioritization I mentioned before, it allows the server to help fix the error for you without you even really thinking about it and without it impacting the user much. So let's say I said, you know what, let's push this image. And unfortunately, I forgot that the CSS is mentioned after this for some reason. I just got it wrong, right? As soon as the server sees that there's a request for the CSS, it will stop filling up the pipe with that image. It will send the CSS, right? The idea is that we're always going to send the most important information as soon as we can, right? So if I get it wrong, the server will make most of it go away, hopefully. It's not magic, though. Okay, SPDY uses one connection. This is actually enabling because this allows us to do all this beautiful prioritization. This allows us to do the server push because we don't have this untenable coordination problem. For large services, when you make 6 connections per domain, it's very unlikely that those 6 connections end up going to the same host. Inevitably, most of them are going to go to different hosts. As a result, if you want to coordinate what's happening for that user session, you're going to have to coordinate the machines that are all terminating those requests. That ends up being really difficult with many connections. Now, having one connection offers other benefits. It reduces buffer bloat. And if you're not familiar with buffer bloat is basically the idea that because TCP is designed to fill up every buffer in between you and the way you're going, that if there's more space in a buffer, it's going to use it. And because it's using it, it's going to increase the latency or the apparent latency over that link as time progresses. And I don't know if any of you have a large buffer on a cable modem or have had that experience in the past. It gets very painful when you're doing VoIP. And the delay with the person you're conversing with increases as you've been talking to them. I think it's really painful. I don't like it. So SPDY, it's helpful. It doesn't make so many connections. As a result, it's less likely to fill up more buffers. It will fill up only as much as it absolutely needs to. If you're a server guy, it's nice, the idea that this thing might use less server resources. Now, there's a kind of trade-off in SPDY. Because we do the header compression, we have a gzip context. So you're going to be gzipping the headers, only the headers, hopefully, on the response. So you're going to be spending a little bit more CPU there. Now, we're looking in the future to change that. We're looking to make that faster, hopefully extremely cheap. But for today, it does use a little bit more CPU only for that part. However, if you have a lot of SSL because you care about security and your users care about security, which is probably why you do, then it might actually make things cheaper because you're going to have to do many fewer SSL handshakes. You're going to have to do many fewer accepts. You're going to have to manage fewer file descriptors. Your kernel is going to have to do less context switches. So there are all of these gains that happen not in the user space of your application, but in the system part of your host. Another thing it allows you to do is it allows you to better measure TCP properties on your connection. So one of those, and perhaps the most important one, is the congestion window. The congestion window parameter for TCP basically says how many bytes in flight you are allowed to have at any point in time. This ends up being important, of course, because this is a form of rate control. And the way TCP works is that it discovers this parameter over the course of the connection. And it starts out relatively small. For most implementations today, it's going to start out around 2 packets worth. I don't know about you, but let's see, an MSS, let's call it 1500, just to make it easy. That's 3K. Most requests don't fit in 3K, let alone the responses. So basically that means that we're going to have to take some round trips in order to open this window up, in order to be able to actually send all the requests so that then we can get the responses. So if we can do something to speed up that part, then we have increased the chance that we have a bigger pipe earlier. So because with SPDY we have the one connection, it gets a better estimation of what this is, because SPDY allows you to have the client cache that setting and tell the server what it was when it comes back in the future. We can open up the pipe to where it was before. Not unfairly, right? We're not doing this arbitrarily. We're doing this based on what the internet said or what we measured of the congestion over the path for that particular connection at that time. I think that's really cool because it means that I'm not limited to sending 3K of requests for that first thing. I can send however much the CWIND eventually got to. Okay. As a result of all this, in case we are writing load balancers, for instance, we use fewer packets. We use fewer packets, of course, because we're doing compression, and we use fewer packets because we're using one connection, and as a result of doing one connection, we have more full packets. So we are not forced to fragment the packets because they're going to the same place. SPDY doesn't require rewriting your site. You do not have to change the URLs. They remain HTTPS and HTTP. Those schemes, I'm afraid, are likely to be here for a very long time, regardless of what is spoken underneath. And the way it works is that when a connection is made, in particular an SSL connection, if your browser speaks SPDY, it will advertise to the server in an extension called Next Protocol Negotiation. I speak SPDY 2, SPDY 3, HTTPS, WebSockets, whatever else it speaks. And the server can then respond saying, I have selected SPDY 2. And as a result, we get a 0 additional latency handshake that allows us to negotiate whatever protocol we want. Now, this isn't SPDY specific. This is just a fallout of the work that was done in order to enable SPDY. But it's nice because it gives us a path forward. It gives us a path on a port that allows us to do new things and to stop this ossification that seemed to be happening on the web, right? We want a web that's continually fresh, that renews, all the way down to its roots if we can. So, all of this prioritization all of the multiplexing. We figure most of this can help your site. But there's that server push thing. And server push might take a little more effort. All right, SPDY isn't magic. I've just described what it is. Hopefully, you're already thinking about scenarios where it may not work for you. But in any case, here they are. SPDY isn't going to work for you very well if you have a whole lot of third-party domains. And what I mean by third-party domains is domains that you do not control the servers, you do not control the content. Right? The more connections you have, the less likely multiplexing and prioritization and all this fancy stuff is likely to help you. The more cold start connections you have, the less likely SPDY is to help you. And I'll point out, when you have a lot of cold start connections, it generally means you don't have a lot of ongoing engagement with your users. So I'm hoping that I've guessed right and that you guys want more engagement with the user, and you want that user to be sticky to your site for as long as possible. So the protocol is designed to help when that happens. All right. Oh, of course. And if you've optimized your site so much that you don't actually have to, use a lot of requests, it may not help you. It can, but it may not. All right. So just to go over it, HTTP has a bunch of limitations. It's not secure. It doesn't compress all that redundancy in the headers. It doesn't do multiplexing. It's only half duplex. It doesn't do prioritization, so if you get the order of requests wrong, well, oh well, it's not going to help you. No server push. Know what you're leaving. And of course, because you have to do all that domain charting, which I find annoying, it requires you to do more DNS lookups. And of course, it requires you to make more connections. All right, so aren't browsers getting smarter? Yeah, they're getting smarter. But they're still going to be worse than what we can do with SPDY. All right, so why do I say that? I say that because each connection that you make has a cost. And if we think back to the beginning, we're using 12 different domains on average. We're using 84 different requests. That's going to require a fair number of connections. And each one of these connections requires a DNS resolution. And looking at data, for a large percentage of people, that's more than 100 milliseconds right there. Just the DNS request. All right, requires a new TCP connection, which requires a three-way handshake. All right, you get the SYN, SYN-ACK, ACK. Okay, that's another RTT. If you're using HTTPS, and it seems like we're going towards that more and more, then you're going to have another few RTTs. And of course, these connections aren't free. The resources for them don't show up out of thin air, right? We have to pay for the servers that are making these connections. So we want to limit them if we can. And of course, something that everybody forgets about, including me, which is why we have these slides. Every connection you make takes up space in an address translation table on a NAT box. And these NAT boxes get really funny when you start overflowing these tables. And what ends up happening, this is super annoying, by the way, what ends up happening is that it doesn't bother to send you any packets anymore, and it doesn't bother to forward the packets anymore. That means it doesn't even close the connection. That means that you're now making requests into a black hole. You've put your connection in dev null. It's gone. All right? So we have to be kind of careful to not overflow these things if we can. Now, SPDY can help a lot there, right? We're talking about a factor of, hopefully an order of magnitude decrease in the number of connections we use today. And if we continue to use SPDY for other protocols, if we continue to use SPDY for HTTP, HTTPS, hopefully something like WebSockets, we're going to have less problems in this area. All right, so what can you do? If you're a system administrator, and this is a complex issue, try and optimize your cert chain. And I'll point out that every single one of the things I'm going to talk about here, with the exception of some DNS stuff, is going to be helpful for you regardless of whether or not you're optimizing for SPDY. When you're optimizing for SPDY, you end up optimizing for HTTPS as well. So ask your cert provider hard questions like, how many browsers that are out there right now have you as a trusted cert provider, right? The more browsers that are there, the fewer certs in your cert chain you have to send. Now, typically, I think we see a cert chain of around 3, which means that we need three certs to get to most of them. But we can get more cute than that. If we're doing SPDY, we see SPDY's been negotiated. We know it's either Firefox 13 or something, or a Chrome browser. But both of those are fairly modern. Thus, we don't have to send all of that data. We don't have to send that third one, definitely. We may only have to send one cert. And as a result, our handshake gets smaller, the amount of bandwidth we spend is smaller, and this happens whether or not we're using SPDY. If you see the NPN is there, even if you don't want to do SPDY, you can change which SSL certs you send. So because we deployed SPDY, we might speed up HTTPS. Competition, oh well. Okay. You can change your TCP settings. If you have a modern Linux kernel on your server, this may be done for you already. The trunk for Linux and some of the versions, I don't recall exactly which, unfortunately, already have an initial congestion window of 10. But here's the magic command to set it. It's IP route change default via whatever is your gateway, IPCWInd 10. And that magic invocation will set it to 10, which, according to Google research, seems to be about right. All right. You also want to turn off this TCP slow start after idle, which, despite the way it sounds, I mean, it sounds like it should be nice, right? I mean, idle, geez. I mean, if my connection has not been doing anything for 60 seconds, yeah, let's quit out. Unfortunately, it doesn't always end up that way. The connection can be idle for 1 packet worth sometimes, and it can cut the CWIN down all the way back to the beginning. Ow. We probably need to rethink this thing. But for now, you can just turn it off using that command. All right, DNS. This one gets complicated. SPDY can share a connection on multiple domains. But it requires 2 things to happen. It requires that the resolution for the host that you're going to go to next overlaps with the IP of the connection that you're connected to right now, and that the cert matches. Got it? Good. All right. So, profit, right? Fewer connections means less latency, means less server utilization, well, rather more server utilization, less CPU, and it's basically a good thing. Don't shard host names when you're using SPDY. You don't have to. You already have a lot of parallelism, right? SPDY has a default parallelism of 100. And it seems like the browsers jack that up as soon as they connect. I think Chrome is announcing 10,000 now for the next version that's coming out, right? So you don't have to shard your host names. Doing so may cause at least a DNS lookup and potentially another connection. Don't need to do it. All right. Try and use server push instead of inlining in the future when support for it becomes a little bit more mature. And support for this is maturing very quickly. I know, for instance, that Jetty has an implementation that does some things that don't require any action on your behalf at all. And in fact, it learns from the referrer what resources end up being associated with stuff. We're hoping that we can make this even better as time goes on and make this even more hands-free. All right. Get a wildcard cert. You should do this because it's cheaper in the first place. And I mean that because if you get one cert, it's most of the time cheaper than getting, 5 certs, 6 certs, however many subdomains you have. It's also good because it allows SPDY to share the connections. Remember, SPDY will share a connection when the IP overlaps with whatever connection it already has and when the cert matches. A wildcard cert matches more than one domain. That's great. All right. Just to let you know on standards. Hopefully, because of us, HTTP 2.0 has been kicked off. And we have proposed SPDY as one of the inputs to this standard. So we're hoping that we end up with an HTTP 2.0 that gives us many of the things that SPDY gives us today, hopefully all of them. Okay, so the future. We don't think we're done with SPDY. I believe that we'll be done, at least at the application layer, when there is no dead air on that connection at all. And at the end of that sending of data, the page has been delivered completely to the user, right? We're not there yet. We use multiple domains. We use multiple domains that have different certs. We use multiple domains that have different certs that end up going to the same server. So we can do better. We can push the SSL certs. We can also push the DNS information. And pushing the DNS information gets really interesting for other reasons. If you have a CDN, for instance, you can do much better geolocation. You can make that connection. You can change where the user is making that connection to something that's significantly closer to your resources. And thus, you can decrease both the amount of work that's done by you, But also you can decrease the latency, which is, of course, why we're talking about this. All right, so as I mentioned before, we got Chrome supporting it, and we have Firefox supporting it. And I'll point out that that's a lot of users. All right. Now on the server side, of course, Google sites use it. Any App Engine sites using HTTPS use it. So if you have an App Engine app that uses HTTPS stuff, you're already using it. You don't even realize. Twitter uses it. Akamai has announced that they are going to support it very soon. Has a technology preview starting very soon. And next quarter, they say that they're going to have it out in production for everyone. Cotendo, Nginx, F5, Jetty, ModSPDY, NodeSPDY, Momentum, etc. OK. So let's get some more good stuff. So here we have a page we want to optimize. And you'll see as I'm moving the cursor around that it seems to be made up of a whole bunch of tiles. You're right, it is. It's 640 tiles. Now hopefully this is going to be more resources than your average web page today. And obviously this is going a little far. But I'm here to show you, to make a point. So here we go. Now, I have conditioned my local host to act kind of like a mobile connection that we would get today. It's a megabit 200 millisecond RTT. Let's see how this loads. This is 8-way domain sharded. Not too speedy. All right, let's try it again. This time we're just going to use Speedy. We didn't do anything fancy. We're not doing any server push. I didn't modify the site in any way. Let's see what it looks like. Yeah, it seems to be going better. You'll notice that it got faster as it loaded more resources. That's that opening up of the TCP connection that I was talking about. If I load this again, it's going to end up faster. But I have more interesting things to show you, so I'm not going to do that. All right, so I told you about server push. So I imagine many of you have imagined you might do something like this. You might decide that, you know what, I'm just going to tell it should push all those resources. If you look at the timings, by the way, that was a lot faster. All right, this is my favorite. You know what? I don't really care about how quickly the full site comes there. I only really care about the above the fold time. I care about the amount of time it takes before the site becomes useful to the user, before it becomes attractive for the user to use. So why don't I do this? Oh, sorry, pushed the wrong button. Why don't I push the resources that are important first? Let me do that again. I'll make a note. Personally, I think Speedy is important. You know, I kind of helped invent it, so there you go. All right, and that's all I have. I'll take questions for 2 minutes, and then I'll let somebody else fill the time. Any questions?
You talk about running segments of the same IP, I take it. So you say, well, what's that going to do with database virtual hosting for SSL sites? I don't know what the browser capacity is like these days.
Gotcha. So one of the things that's great about Speedy is that you're guaranteed that if anybody supports it, and actually you can just look at it from the NPN perspective, if anybody supports NPN, you know they're a modern browser. You know that they do the TLS thing that announces the name as part of the TLS handshake. You don't have to. So if the SSL, if you don't have NPN in the SSL extension, it just ends up being HTTPS. So it's fully backwards compatible.
Yeah, but I'm saying, you say to run all one site on the same IP, different domains. So you don't know what domain to serve because you might serve the wrong SSL certificate. You could use some again, that doesn't work.
Right. Any other questions?
Why not HTTP over TCP?
We looked at that. SCTP has some problems for actual deployment. In particular, it deals very poorly with NAT boxes. A lot of the things that we designed for with SPDY were inspired by things like SCTP and Beep.
But it gives you multi-homing and high availability, which I think is not there in SPDY right now.
That's correct. It doesn't give us multipath. Now, in reality, I haven't actually seen SCTP give us multipath either, though. I would really like for it to. It's just very difficult to deploy for real. And in this case, we're trying to deliver something that we can deliver very widely.
All right, thank you.
Specifically about the congestion window caching, I know you guys online have talked about the potential issues around forging that and issues with the connection changing between requests. But I guess what hasn't been clear to me is the connection window sizing like a requirement? If a browser sends it, are you required to start with the number they want? Is it a shall or is it a hint?
It is a hint.
Okay.
Yeah.
How does SPDY handle termination of SSL at the load balancer if you have a hardware load balancer that's passing to the back end?
If you have a hardware load balancer and it doesn't support SPDY, you're not going to be speaking SPDY. So the way it's going to be handled is hopefully eventually many of these vendors will be supporting SPDY. And having gone around and talked to a number of them, I can't promise anything, I'm not the vendors, but it seems like there's interest.
How is the priority defined for these local default stuff?
There's a bit field that's in there, and basically the lower the number in that bit field, the higher the priority. Probably should have done it the other way around because it gets confusing, but that's how it is. I know there are at least 16 different levels of priority. We might decide to change that at any point in the future, but if we did, it would probably just be to increase it. All right. Oh, one last question, and then I'll yield.
The other thing would be, is there any point to doing push versus inlining? Like normally for HTTP, you do inlining so that you don't get the round trips. Is there any point to push with SPDY since it's already doing that RTT compression?
Hopefully you are optimizing your site for the whole experience and not just the first page load. So if all you're doing is the first page load, you're right. So long as you get the inlining right, which is another problem, so long as you get it right, it's going to be basically the same as server push. If you get it wrong, it's not. If you have resources that could have been cached but aren't because data URLs don't allow you to do anything like that, then server push is going to end up better the second page load, even when they come to it anew, and it's going to be better on the second, on any portion of the session after that. Last question.
Okay. For a scenario where you have browsers which you can't really change, at least not in a short amount of time, like embedded systems, would a scenario like a client-side proxy of HTTP to SPDY actually be worth it?
Do you mean a proxy from SPDY to HTTP, so SPDY on the client side?
The other way around, actually. The browser
both can work.
does HTTP requests, but they get out of the embedded equipment in SPDY.
Both can work. SPDY is going to be most advantageous when it's used over the higher RTT link. Mm-hmm. So if you're speaking SPDY directly to your server, because there's a load balancer in front of it that's speaking SPDY to your server, the benefits in terms of latency aren't going to be there. But if that proxy is close to the client,
on the setup, then
you will see benefit, hopefully. Thank you very much.